Thanks everyone. This is Rifat Sipai, a faculty member at Northeastern University, Department of Mechanical and Industrial Engineering. And today I would like to provide you a brief demo on using MATLAB Simulink PID Tuner utility. For this demo, I'll be assuming you already covered transfer functions for open loop systems as well as closed loop systems. You have studied how system poles affect transient response characteristics, and you have an understanding of how to select controller gains to be able to render a closed system to have particular pole values. So with that understanding, now what we would like to do is we'd like to utilize the PID tuner to kind of semi-automate the tuning process. I'm using here a MATLAB's online version. So if you log into mathworks.com using your student account, you can go on the products and access the online version. So I'm gonna go to full screen here, and I'm gonna demonstrate this on this feedback control system where I have a transfer function which may represent an MCK dynamics. And the input of this MCK dynamics is force in this example, and then the output is displacement. So we can just put that here just to keep track of things. And then we are applying a step function of unit height, and it will jump from 0 to 1 at time equals 1, and we would like that the displacement will track the step function. And obviously it's because this function is discontinuous, and because we have inertia, it will not be possible to perfect track it, but the system will seek to reach the steady state step function if you design the PID controller gains properly. Right. Overall, the tracking error is computed, and the PID controller will then decide how much force they apply to the system, and the system will react to that, and then this loop will keep updating or refreshing, and 1 millisecond at a time. And the way I set this up. If you want to change the model settings, you can also go here, and you can change the step size here. At least 1 millisecond step size is going to happen in the simulations. If you want, you can tune these numbers. So at least every 1 millisecond is going to be an update in the simulation. All right, so now let's get to the PID gains. So here, what I'm assuming is that you already designed your PID gains based on some criteria you have for a displacement profile. For example, you have maybe a settling time requirement. Maybe there is some maximum overshoot you can allow, and maybe 5%, 2%, who knows. And then you develop the closed system transfer function, and you did what we call a pole placement procedure to find maybe a candidate set of PID gains. Now you want to refine those, and maybe you want to maybe search for better gains that will give you, what I mean by better gains is that something, a set of gains that will give you maybe a more desirable displacement dynamics. So now we are at that stage, and you build this, let's say, closed system, and then you enter your PID gains into the system. And so this PID block comes from the continuous library on the far left, and now we have 3 gains we can enter here, PID gains. Let's say somehow you found these gains as your initial gain values through some pole placement procedure, and n denotes the filter coefficient that helps you the approximated derivative actions here. So n equals 100 works really well. And if you happen to have a different type of controller, instead of PID, you may have PI, PD, P, or I. You can also select those from here. And then I'm going to be using a parallel representation. So the formula of the PID controller is given here. But if you are using, say, the ideal representation, then the formula will slightly modify. And more or less, it's the same effects, but the roles of the gains will be slightly different. So I'm going to go back to the parallel representation. All right, so let's say you have these basic gains that you have designed, and you say okay, and then you can double click your scope, and then we can run this, and then get a response like we see on the screen as an example, right? So here as an example, let's say we have about 30% overshoot, and maybe that's too much. We want to improve that and reduce that, and we have a settling time of approximately maybe about 1.5 seconds or a little less, and maybe that's something also we also maybe want to improve. And right, so all right, so now we say, all right, we want to make this maybe better. How do we do that? Let's go to the PID controller, and then in this box here at the far right, there's a tune button. You hit that and it will pop a new box, a new window on which you can actually start tuning the PID controller. So idea here is that the tuner will automatically tune, and you can also change the tuning parameters, and then it will show you a comparison before and after. And so there are at least two things you can do here. One is to mess with the response time, so you can have a slower dynamics, the solid line, versus faster dynamics, again, solid line. And you can also play with the transients, and I suggest staying on the robust side, not the aggressive side, because if you go to the aggressive side, it will become more oscillatory. Again, the solid one is the new one, is the one that's refreshing right now. And as we are changing it to be more aggressive, it becomes more oscillatory. So I suggest staying on the robust side of things, and then you can play with the dynamics in terms of the time scale. So with the faster or slower response. Okay, right. So obviously, a faster response comes with a cost of more power demands, and that we can maybe discuss another time. So keep that in mind, and it doesn't come for free. But if you have more power and you're able to do a faster control, and this tuner will help you to find the PID gains that will actually render a particular behavior from the system. Now, what we can do is we can actually click here, show parameters, and we can actually see the solver is actually running a simulation and simulates the PID gains as you play with the knob, and then instantly will update the PID gains as well as the corresponding transient characteristics. Right now the overshoot is about 10% after the tuning. It was about 30 before I started, if you remember, and settling time is 0.2 seconds. It has gotten a little worse than what it was before, but the overshoot has dramatically improved. And so we can actually investigate whether we can make this a faster dynamics with also less overshoot. So that's also a possibility. If you pay attention here, we actually achieved faster dynamics, smaller settling time, and much smaller overshoot at the same time. So the tune block, the solid curve, is what we're gonna get after the tuning operation. Say you like this, then you're gonna just hit update block, and the PID gains will be carried into the PID block that we have here. So we can close this, see the numbers have changed, and then you can say hit OK, and now we can run this. And obviously we should get what we designed for, because the designer uses simulations anyway. So here now we can auto scale if you like. We can have a look, and we have now about 10%, a little more than 10% overshoot, better than what it was before. And if for some reason, if this doesn't please us, we can always go back to the tuner and then play with the numbers. Now, there are several other things you can do here with the PID controller. You can maybe explore those as you become more proficient, but at the minimum, I would maybe want to mention saturation. Saturation actually allows you to dictate what comes out of the PID block and to dictate that variable to have certain limits. So if the force is 1000 newtons, but your actuator in real world is not able to apply 1000 newtons, then you actually want to saturate that. You want to clip that so you can actually limit what comes out of it. In the context of this problem, because output is force, here's an example where we are limiting the actuator to apply a force anywhere between plus minus 50 newtons. If the PID demands to apply more than 50 newtons, only 50 will pass. Or if the PID wants to apply more or less than minus 50 newtons, only minus 50 newtons will pass to the system. So it's gonna, the force is gonna be clipped if it's out of range, and if it's within range, it will pass as is. So if you actually use saturation block, and if you hit OK, there's gonna be a little tiny symbol here which represents saturation. You will see that over there. So if you see that, remember that the force is being clipped. It means you're not free to apply any force you want, and that obviously clipping is going to limit your ability to control the system. So let's have a look what happens if we actually clip the force. Is it going to be a problem or not? And it has become a little bit of a problem because we can see the overshoot has increased just a little bit. And what we can do is we can actually put a scope here and investigate, right? How much of force are we sending and when is it being clipped, right? So let's have a look at the force. Let's run this. Let's see when it gets clipped. You see here, there was a little clip here. The PID demanded a larger force than 50 newtons, but the saturation blocked that and only allowed 50 to pass. Obviously, if you start limiting the range of outputs you're able to send out, then the control ability will become worse. So for example, if I don't allow anything outside the range of 2020 plus minus 20 and clip the force at 20 newtons plus minus 20, right? And if I run my controller now, I will notice that there's going to be more issues with my control effort. Now the overshoot has become much larger, because my controller, although it wants to send more force, the saturation doesn't allow it to send more force, and for that reason the control performance becomes not as good as we hoped. And we can double click here and check the force profile. You can see the force has been clipped, right? Whenever the PID demanded more than 20 newtons, it only passed 20, but luckily for a short amount of time. So this condition has been violated for a very short amount of time. So therefore the control performance hasn't deteriorated significantly, but depending on the circumstances, even in situations you may actually see instability because of the saturation effects in the system. So although you design your PID gains properly, because saturation, the closed system may end up being unstable. All right, with that, I end up here. Thank you for your attention, and hope you have fun.